You might notice up here it already says study this information you're going to take notes on tonight. Hint, hint. You know what that means. We're not going to get through all of these terms today. We're probably not going to do these last three, but you can still leave space to define them. What we're doing now is we're trying to answer this first question. What is electricity? You'll have an answer to that by the end of this period, and you'll have a real understanding of it by the end of next week or so. When we look at electricity, we're going to look at two kinds of electricity. The electricity we use from a wall outlet or we get from a battery, we call that current electricity. That's the useful electricity. And the electricity we see naturally occurring in the laundry, on your socks, in the sky in the form of light, we call that static electricity. And we're actually going to explore this one first. We'll be getting into that the next few days, looking at lots of cool demos and understanding static electricity. We're going to talk about how a light bulb works today, how a circuit works, and where electricity actually comes from. What actually is it? When we're done with that in a couple of weeks, then it'll be magnetism, and then we'll talk about how to be able to answer all those questions. Okay? Now, on the in-class assignment yesterday, I had you draw circuits. I call them circuits. And I want you to get a definition of what a circuit is. And if you look at these four illustrations, this is what you should have drawn. You might have drawn it on the side, but this is what you should have shown me. And you see there's a pattern there. The bulb tip touching the top, tip touching the bottom, side touching the top, side touching the bottom. All four of those share something. They all have something in common, which is how they got the name circuit. C-I-R, circuit, like circle, or circus is a big ring, okay? And it means to go around. That's not the definition I want you to write down, but that's where the word came from. And in every one of these examples, you can trace the flow of electricity in a circle. Put another way, if you follow the flow of electricity, you will wind up back where you start. Just like running around a track. You'll come back to where you start. To get a better look at why these are called circuits, that path, I want to show you this little simulation here. So we see a light bulb. Now it's blown up so we can see the parts of the light bulb. We can see that the tip of the light bulb connects to one wire coming inside. And that the threads, the grooves of the light bulb, connect to another wire. And they stick up inside the bulb like this. And in between those 2 points is this curly wire called the filament. And when I turn this circuit on, we can see the electrons flowing through the circuit. Electrons are why electricity is named what it's named. Electricity is the flow of electrons through a circuit. There's your definition. Electricity is the flow of electrons through a circuit. You're going to know that so well. I'm going to have you saying that back to me almost every day from here on out. Electricity is the flow of electrons through a circuit. That's what the little red dots you see moving here represent, electrons. A circuit, then, is a complete path for the flow of electrons. That'd be your definition for a circuit. A complete path for the flow of electrons. Do I have a complete path now? No. When I open that switch, the electrons can come through here, through the battery, but they can't complete the loop. If they can't get back to where they've been, you don't have a circuit. So all four of those that I had illustrated on the previous slide were all circuits because it was a complete path. Now, Let me give you a little background on the light bulb. I think you might find this a little interesting, because the light did change the way we do a lot of things in the world. Who invented the light bulb? Who's given credit for inventing the light bulb, I should say? Thomas Edison. Which one is he?
The second one.
This guy right here. Even though this guy's shown the light bulb, these two actually worked together for a while, and then they were bitter rivals after that. We'll talk about that later. There's Edison in his workshop in Menlo Park, holding one of his light bulb designs. You know, before that, we had light that required chemical reactions, of course, candles. It was expensive. Couldn't put it into your average home. He was trying to come up with a device that was so simple that it could go into any home and it would be reliable, produce light for a long time. And what we know is that when we run those electrons, the electricity, through certain substances, they will heat up. And with the heat, you also get visible light. They will glow, just like a fire produces visible light. That's not technically on fire, because for fire we need oxygen. But it does give off heat and light. And what he had a difficult time with, it took a lot of perseverance on his part, he had to come up with the right material. So we got our two wires coming up inside the glass ball here. But what material do we use here? Again, for the filament. And he tried all sorts of things from, you know, wool, human hair, cotton, to other materials. And what he kept finding out is that when you ran a lot of electrons, we'll talk about the electrons later, a lot of electrons through that wire, it would heat up and it would produce light, but it would eventually heat up so much that it would melt through. We say the light bulb burned out, right? And his early bulbs, they didn't give you much light, they made a lot of heat, and they would burn out in a short period of time. We eventually happened upon a substance known as tungsten. Tungsten is an element you can find on the periodic table that has a high melting point, which means it can get very, very hot before it melts and breaks. So that's what we use now for the filament. Now a filament, what a filament does is it will resist the flow of electrons, and when it does that, it will produce, oops, that's I and G, making two things, heat and light. And a light bulb was a huge improvement over a candle. Candle, you get a lot more heat than you do light. A light bulb still is less than perfect. For what we put in, we get about 10% of that energy gives us light. That's a lot of wasted energy. Now, you don't turn on an electric light to get warmth. You turn it on to get light. These lights, fluorescent lights, for all the energy you put in, you get about 40% of light comes out of that energy. So it wasn't the most efficient, but that was the design. So the two things is coming up with the right material to use for this filament, and the second one was getting rid of the air inside here so that that wouldn't burn out. It wouldn't actually catch on fire and melt quicker. Nathan?
What about the light bulbs that are like basically heat?
Those are compact fluorescent, so they work on a totally different principle than this. They do have a filament, but it actually causes light by causing the gas to get excited. So it's a different principle. Yeah. All right. Again, to kind of understand what's happening here, when the electrons go through, this is a big, thick wire. When it gets to this filament, it's a tiny little wire. You look at the little filaments inside light bulbs, they're tiny little wires. Imagine this. Imagine this as like I-10. And all of a sudden, I-10 goes from being I-10 goes from being 4 lanes down to 1. Can you imagine what's going to happen to all that traffic? All of a sudden, it's going to be squished together, and if the cars aren't going to slow down, they're going to collide, and there's going to be friction, right? Well, it's not exactly friction, but when all those electrons try to squeeze through this small little space, we get heat. And if I could heat up my hands enough, they would glow. That's the glow we're getting here, okay? It's from that energy. And I can show you my own little homemade light bulb over here. Probably was like some of his early designs. I haven't yet come across any tungsten wire, so I'm just using plain old copper wire. Copper wire is not a bad conductor, it's a good conductor. It does allow electrons through it easily. So the problem with this one is it takes a lot of energy and it doesn't give me a lot of light. If I could suck the air out of here, if I could use something like tungsten that wouldn't melt so early, I'd get better results. But I can get a light bulb for a short time. See what happened? That was it burning out. It broke because it melted the wire in that spot. So that's kind of like Edison's early light bulb. All right. So, back to this one. That's the early light bulb. And now you know you should have a definition for a circuit, you should have a definition for electricity. Electricity is the flow of electrons through a circuit. A circuit is a complete path for the flow of electrons. Matt? No, but you can trade for one over there. Okay, what we're going to come up with here is a list. You're going to help me generate this list of different forms of energy. And we just talked about one. One of the most common forms of energy is, what are we studying here, guys? Electricity. You know I'm going to ask you to give me some of these back tomorrow. So you want to start finding ways to remember these. The name of our unit is electricity and magnetism. That's another form of energy. Where else can you think of different forms of energy that, something that can do work or is doing work? Wind. Moving air is a form of energy. Do you know that we have enough wind energy available in this country that we could put up a whole bunch of windmills, like the windmill farms they have on the way to California? That we could provide all the electricity needs for the entire country. We wouldn't need any oil, wouldn't have any, factories burning nasty stuff and putting it into the air. Of course, it would cost billions of dollars to build these, but once we have it, free energy. Yeah.
Hydro.
There you go. So hydro just literally means water. So what we want to have here is moving water. Air by itself is an energy. The air is moving, it can do work. Water sitting here in this container is not doing work. If it's moving, it may be turning a wheel or something, now it's doing work. So moving water would be another form. What else?
Oil.
Say that again?
Oil.
Wheel?
Oil.
Oil. What do you mean? I'm thinking of something that's doing work. It's actually hard to describe when I say form of energy. Yes? Nuclear. Or you could say atomic. Either one would be fine. Absolutely right. You're made up of atoms. And the atoms are held together by bonds. And if we could break those bonds, it releases a tremendous amount of energy. Or if we can fuse atoms together. So the atomic bond is a tremendous amount of energy. What else? Yeah. And I wouldn't just say sun, I'd say light. And we say solar power. Well, your solar powered calculator still works inside off of electric light. So light is a form of energy. Yes?
Fire.
Yep. Heat. Because fire includes light as well. So this would be the heat part. Heat is a form of energy. 3 more, so we come up with them.
Steam.
Steam would be moving water vapor, actually. So we already kind of have that one. It's a good guess, though. I'll give you a hint. One of these is the form that you are experiencing right this very second. Oh, then it stopped. Then it started again. Then it stopped again. But then it started again. It keeps starting and stopping.
Door.
No?
Did I say it the first time?
What? No? There it was. Now it's gone. It was there, then it's gone. There it is. Sound.
There's the door.
Or vibration. S-I-O-N. Sound or vibration. Okay? I was talking about my speech every time I talk, you're experiencing it. That's a form of energy. Vibration is just such low sound waves that you don't hear it, you feel it. Some animals can hear it. Elephants can communicate over miles with the sound of their feet hitting the ground. They don't hear it, they feel it through vibrations. That is a form of energy. Okay, we're almost done. How do I get electricity out of this battery? What form of energy is stored in there? What makes this work? What's inside the can? I know some of you know. Huh? What's in a battery that makes it produce electricity? Come on, guys, you're doing so well.
Chemicals.
Chemical! Chemical energy. You combine some chemicals together, you get heat, you get light, you get an explosion. One more. Come up with most of the hard ones. I'm not even sure which one it is we're missing. What are we missing? Oh, I know. Okay, the last one people rarely come up with, and that is mechanical. When I say mechanical, you think of like a mechanic works on a car, a machine. Anytime a machine is moving, you have mechanical energy. And your body can be a machine. So when you go over and you crank the handle, okay, you're doing work. That's called mechanical energy, okay? Movement of a machine. So you should be able to come up with many, if not all of these for me tomorrow. Now, the thing about this, and the reason I'm showing this to you now, is that electricity is only as useful as what we can turn it into. We don't use electricity as electricity. The outlet over here has electricity available. If I said, ooh, I've got electricity, you'd be totally unimpressed. Head up, please. Because that outlet does nothing. It's when I plug in the stereo to it, and it converts the electricity into sound, that I get something useful. So what we do in electricity and electronics is it's all about taking this and turning it into one of these, or taking these and turning it into that. If we're not making a change, electricity by itself is useless. Let me give you another example. The computer here, it's plugged into electricity, and the box can do all sorts of stuff with electricity. But if it wasn't for the monitor, it'd be pretty useless to me. I need to see. So that converts electricity to light. I have my computer hooked up to the stereo over here so that I can convert the electricity to sound. I have it hooked to the printer. It takes the electricity and it moves a machine. What kind of energy? Mechanical energy to write the images on the page. I have devices that go the other way. I have a device that takes sound and converts it to electricity. What's that called? Microphone. I have a device that takes chemicals and converts it to electricity. What's that called?
Battery.
Battery. Okay. I have a nuclear power plant that takes atomic energy and converts it to electricity. Okay. I have hydroelectric dams that convert moving water to electricity. I have light bulbs that go from electricity to light. I have devices that make all these changes, but without making the change, the electricity by itself, just sitting there in the outlet, is worthless to me. I have to turn it into something else. Okay, Sky? Alright, so that's what this card says down here. It's only useful if we change it. And that's a big part of science, is making changes from one kind of energy to another. Now, here's my little political comment. I'm required to teach you guys what they call standards. Okay? It's all this big thing that the state has decided you need to know. And if you look at the standards all the way up to 12th grade, try to find this law in there. It's not in there. And I think it's kind of sad. I'm glad I teach it to you. You should be glad I teach this to you, because it's like, oh, I'm just going to skip gravity. They don't need to know gravity. That's not important. Okay? That's kind of an important science concept. So is this one. Even though it's written down here small, I still want to make sure you have this down. This is called the First Law of Thermodynamics. I'll write it nice and big for you here. Thermodynamics. First law of thermodynamics. Thermo means heat or temperature. Dynamics refers to change. And this isn't just change in temperature, it's changes in any of these kinds of energy. And what this law says, the first law of thermodynamics, is that we don't create energy and we don't destroy it. All we do is change it. Okay? We can't create or destroy energy, we change it. When we release the bonds between atoms, we change it from atomic energy to light and heat and sound. We don't make something new. And the energy doesn't go away. When we use a battery in our stereo plates, it converts it into sound. It doesn't just go away and suck up the battery and just go to nowhere. It's changing constantly. And this is the way the whole universe works. You can trace the energy all the way back to its source. In our case, what is our main source of energy? Right here, right now. Where did your energy to write your notes, to use your brain right now, where did it come from? I'm saying trace it all the way back to the source. What can you trace it back to? Give you a hint. 3 letters. The sun. Very good. Let me show you. The sun produces atomic energy when atoms of hydrogen bond together and make helium. That atomic energy releases light and heat. The light and heat travel all the way to the earth. Shine on the earth, warm up the atmosphere, shine on the plants. Plants grow. Animal eats the plant, I eat the animal. When I eat the animal, I take that meat and I convert it into chemical energy stored in my body. That chemical energy then allows me to produce electrical energy, to send signals to my neurons, to think a thought, to send signals to my muscles to make them move. My muscles move, I talk to you right now, that's mechanical energy, and that all could be traced back to the sun. All we're doing is changing the energy. Okay? That's why it's such a big concept, so important. And I want you to start looking around for all the devices that make these changes. You know, like the light bulb and the heater and the windmill and so forth. There are others that you probably didn't even know existed. You know, I talked about being on that deserted island and making yourself electricity. Well, there's some surprising ways that you can make electricity. If I have a heat source, I can make electricity. Now this is not going to be enough to power my radio, but I can in fact make electricity from heat alone. All I need is this little device here called a thermocouple. Thermo means what? Heat. And couple means to hold together. You see where these two pieces of metal are held together? I'm going to heat that up, and when I do, you look at the meter there, and you'll see the reading go up. I'm making electricity out of heat. Now, again, that's not going to be enough to power my radio. Why is it still on, by the way?
Because the probe is still on.
No, because it's still hot. Okay, and it's cooling off. And once it cools off to room temperature, that'll go back to 0. Okay? I'm not going to be able to power my radio that way, but I could use a device like this, a thermocouple. Takes heat and turns it into electricity. I could use that in, like, say, a fire alarm. It could detect flame and set off a fire alarm. Okay? Another cool device that changes from one kind of energy to another is something called piezoelectricity. That's actually a technology. Piezoelectricity. If I told you you could make electricity by stirring pudding, would you believe me? Good. You should believe me. You can. If I told you you could make electricity by chewing candy corn, would you believe me? If I told you you could make electricity by banging rocks together, would you believe me?
Yes.
Right. You can. How simple is that? This is an interesting property of certain rocks. This rock is called quartz, more specifically milky quartz. You might have this in your front yard. You can try this yourself, but be careful. wear eye protection. So you go home, you get yourself 2 pieces of milky rock, milky quartz like this, go into a very dark room, as dark as you can get it, and bang the rocks together in front of your eyes. Make sure you have eye protection, okay? And you will see flashes of light. Not sparks, not in between the rocks, but inside the rocks. Those flashes of light come from high voltage, a lot of volts, created by banging rocks together. That's a pretty simple way of making electricity, okay? And that's called piezoelectricity. I'll get to it in a second. It's taking vibration and making electricity. Converting vibration to electricity is piezoelectricity. Yes?
Should we omit lightsaber?
Someone else was asking about that earlier. Well, that of course is in quartz. I don't know if that works on piezoelectricity. I'd have to research that really. I'm not sure. But what I really like about this is, of course, that's not all that useful. Flashing rocks, whoop-de-doo. It's not like it's going to light your way. Okay? But what you can do is you can use it in other devices. Recognize this? No, it's not a button. It's a barbecue lighter, exactly. You want to try it out? Come on up. So you're going to put this in your mouth. In your hands, there. No, the metal part. No, this part there. Metal. No. Okay? Well, I don't know. There. Okay? This is what I call my automatic blinker. Go ahead and try this one. Watch his eyes. We'll see if it makes him blink. Oh, kind of a little bit. Well, a little twitch. He's fighting. Here, you want to try? Want to try? Squeeze it. Come on. There. See? Automatic blinker. I'm producing thousands of volts, guys, by banging on a piece of quartz crystal. Hitting it with a little plunger in there is what's doing it. A little spring-loaded thing hits it. Okay? Thousands of volts. Enough voltage that it can jump across this gap of a 1/4 of an inch or a 1/2 inch. That takes thousands of volts to do that. Okay? From banging on a rock. It's the same thing they use in these guys that you light your candles with. A little spark jumps across there, and the gas comes out and it lights the flame. Or my special little creation here. Look at the button. Look at the button. Look at the button. Just because I'm grinning that way. Right.
My God. Oh.
Sometimes it'll fire a second time. We'll see. We get it to go a second
Oh my
time.
God.
No. No joy.
Oh my God.
So what we have is that little spark jumps between those 2 screws at the bottom. And all I did is, at the beginning of the period, I put a tiny bit of lighter fluid in there. And I'm trying to create some fumes, and the fumes build up inside the can, and then I just ignite them. I light them on fire with a little spark. That's what sets it off. So piezoelectricity is pretty cool. Here's something I think is particularly interesting. It works the other way. If we can use vibration to create electricity, maybe we can do the opposite. We can. We can take electricity and create vibration. So this little buzzer you're hearing, it's the same basic kind of device you might have in an alarm clock, your cell phone, tiny little speakers. And what we've done is we take a brass disc here, and it's coated with a thin layer of quartz crystal. We grind it up into a powder, and that's attached to the little disc. And then we have our electrical wires go to that, and then we put it in a plastic case to make it louder. That's a piezoelectric sounder, a little tiny miniature speaker, if you will, that uses the electricity to make the disc vibrate. Instead of vibration making electricity, it's the other way around. Nope. Nope. It's not like it's knocking it off or anything. It just gets it excited, and that's the way that material responds. This stuff will last a long, long time. I don't know if it'll wear out eventually, but I've never heard of that. They last a long time. Okay, so those are some of the devices that will do those conversions. Now we're going to go back in time. We're going to go and I'm going to give you a little history lesson on how we got to our understanding of electricity. It starts with the early scientists. Okay, the first scientists were not called scientists; they were philosophers. They sat around, they posed a lot, thought deep thoughts, like, Anthony, if a tree falls in the woods and no one's there to hear it, does it make a sound? And if Matt rests his head on his hand, can he actually think that way? You were doing so well. So that's philosophy. But then they would ponder other things like, I wonder what she's made of. I wonder what the rock is made of. I wonder what the sky, the orange tree are made of. And early philosophers first thought everything was made of different stuff. Okay? There's hair matter, there's skin matter, there's rock matter, there's orange tree matter, and it's all different. And then somebody got the idea, I'll bet some of these things have something in common. Maybe everything's made up of elements. Can anyone tell me some of the early elements that they thought everything was made of?
Fire, earth, wind, water.
Exactly. Fire, earth, wind, and water. They thought everything was made up of combinations. So like if Brianna has a little red in her hair, well then she must be made of fire. Okay? And if Jeff farts a lot, he must be made of wind, right? You got a lot of the wind element in you. Just kidding. But you see what I'm saying? And that sounds kind of goofy. It's like, why would you even think that? But it was that jump from everything is different to things have stuff in common that led us to this. This is called the what? Periodic table of elements, which you should know quite well by the time we're done with our chemistry unit. And what we now know is that all matter, whether it's a star, a dog, a piece of poo on the ground, an orange tree, a rock, you, doesn't matter. We're all made up of these ingredients. Some things have different elements in them than we do, but everything in the known universe so far is made up of these ingredients. We want to whip up a batch of, Brianna, we have to get some carbon, some oxygen, and combine them together in a certain way, and we can make up a Brianna. We want to make up anything, just combine them together. I take a couple of the hydrogens here, and a couple, and an oxygen, and I combine them together. What did I just make? Water. Okay? I just made water. I took 2 hydrogens and 1 oxygen. Yes, you can make water. You can make a diamond if you wanted to in the lab, but it would be a lot more expensive than digging one up. It takes a lot more work. So what you end up with is the shopping list for the entire universe. You want to make a universe, this is what you need, these elements. And then you combine them together. So each element you can see represented here in my illustration by a circle. This is a different kind of atom from this. This is a hydrogen atom, this is an oxygen atom. And we're now showing it in a model. Models aren't perfect. They can mislead you. This is not the way water actually looks. Okay? No matter how much you zoom in, it's not going to look like that. It certainly isn't going to have little H's and O's on it. But it will have 2 things that are similar and 1 that's different, and it will be held together. Where it's held together, right here, you can see on this little model represented by these springs. They use this a lot in chemistry. There are no springs in real atoms, in real molecules. This simply represents a bond. Electricity and magnetism hold those 2 atoms together and these 2 atoms together. That represents a bond. There's nothing really there in real life. Are you with me? Okay. So now what I'm going to ask you to do is to make the jump into this idea of an atom and how it looks and what it works like. But remember that it's not going to look just like this model. The model is not perfect. This page, not just this here, but the entire screen, imagine that as representing one of these balls. Okay? The atom is not round, it's not wood, and it's not salt. So already it's quite different from this. And even if we look at this illustration, it still has some errors. There is a part in the middle. It's not surrounded by a circle like that. But that part in the middle is called the nucleus. The nucleus of the atom is in the center. The nucleus of the atom contains the two largest particles, which are what? Protons and neutrons. These particles are much bigger and heavier than the electrons. So you can almost think of the nucleus of the atom like being the sun in our solar system. Much bigger than the Earth. Okay? And the electrons, head up Taylor, they orbit around the outside. Now, let me just tell you some things that are not accurate about this model so I don't mislead you. First of all, the electrons, you see the size I made them here? If I made them accurate compared to the protons and neutrons, they'd be a dot so small you wouldn't be able to hardly see it. Okay? They're much, much smaller than that compared to these. These have almost no mass and very small compared to those. The second thing that would be misleading is it looks like there's only one path for the electrons to go. There isn't. There could be another orbit out here with electrons in it, out here. Okay? And there could be another orbit out here. We call those shells. You'll learn more about that in chemistry. But the space between the nucleus and those orbits is much greater than I can show on this one board. If I drew, the nucleus of the atom like that big, the electrons would be way out here, off the page. That means that most of the atom is made up of what? What's in here? Space. Empty space. And that's even true for this little drawing. All this in here is space, but it's even greater. There's much more space compared to the size of the particles. Okay? Now, we'll look more at the atom later on down the road, but for right now, what we're really interested in is the electricity of the atom. Because in order to have electricity, we have to have, where does the word come from? You guys are bumming me out. What? Electrons. In order to have electricity, we need electrons. And the electrons come from outside the atom. Those electrons, they don't just spin in nice little perfect circles like this. They spin in complicated shapes, and imagine a beehive. So here's the hive, and here's the bee, spinning some in close, some out farther, in all different directions. Okay? The ones that we're really interested in for chemistry are the ones on the farthest point, farthest outside the hive, way out here. Those are the ones that we're going to get to move. And if we get them to move, we have electricity. Well, first of all, we want to look at this atom and ask ourselves, what is the charge on this atom? To do that, we have to know what each particle is doing. Neutrons have no charge. As far as the electricity of the atom is concerned, they don't get to vote. Protons have a, take a guess, you got positive or negative? They have a positive charge. Pro, you're for it. They're a positive charge. So each proton has a positive charge. Electrons have a negative charge. So once again, positive, neutral, negative. That's why when we write electrons, we often do E minus. That means it's an electron with a negative charge. Okay? Based on what I've drawn here, can someone tell me what the charge is on this atom? Can you tell me specifically what it is? Negative what? Give me a number. There's 3 negatives?
No, I have no idea.
Well, let's break this down, guys. How many negative charges do we have? 1, 2, 3, 4, 5. So we have 5 negative charges, 5 electrons. How many positive charges? 2. So we have a plus 2. So if I want to know the charge on the entire atom, what would it be?
-3.
-3. You didn't see how we arrived at that. Every one of these cancels out one of these. It's one way of looking at it. So that's going to cancel out this one, and this is going to cancel out this one, and that leaves me with 1, 2, 3. -3. A positive and a negative cancel each other out. Or you can make yourself a little number line and jump 1, 2, 3, 4, 5 negative. And then you got to come the other way, 1, 2 positive. That leaves you at -3. I'm going to ask you to do this very same thing on the quiz. Okay? Let me just throw a few more examples, make sure you've got this. What's the charge now?
-2, -1, -2, -3, -4, -5, -6.
Good. People get thrown. I throw out the neutron and they want to change it. Remember, these don't get to vote. I can throw those out all day long and still have the same charge. Okay? These are some facts about atoms that will help you to understand what's going on and why the electrons do what they do. But I want you to know that atoms are not solid. They're mostly space. Like I said, the space between the electrons and the nucleus is much greater. The center of the atom is what we call the nucleus. That's where you're going to find the protons and neutrons. Now, when we have electricity, it's the electrons that we get to move. You could get protons to move, but it takes a lot more work. Remember how much bigger and heavier they are? They're going to want to stay put. In the nucleus, you have two things: protons that are positive and neutrons that have no charge, are neutral. Spinning around the outside, though, you've got the electrons in a cloud, like bees around a beehive. And every one of those has a negative charge. They are tiny in size, tiny in mass, when you compare them to protons and neutrons. So they're going to be a lot easier to move. If we can pull one off, and we can give it a path, what do we call the path for it to flow? A circuit. Give it a path to flow, then they'll start to move. So now we want to look at why. Why do they move? And electrons, just like you, follow certain rules. Will govern when and where they will move. I'll show that to you here in just a second. Here are the rules for electrons. Opposites attract. I think that's the rule for the universe. Certainly seems true for middle school girls. They always go after the biggest loser guys. You know, if they're a straight A student, they seem to be attracted to all the straight F guys. I don't know why that is, but opposites attract, I guess. You and your friend are both stubborn, you might have some problems. You might fight a lot if you're both stubborn. Likes repel. And you know this. You know this rule, even though you may not have called it that. You know that when you put batteries in a flashlight, you put the plus end of one battery against the negative of the next one. You don't put the two pluses together, because if you do that, the electricity won't flow. It goes plus to minus, plus to minus. You know that with magnets, if they're both north poles, they will repel. If it's north and south, they're opposite poles, they will attract. Same rules are for the magnets. And that has to do with the electrons too, which we'll get to later on. Electrons prefer to go to where there are fewer electrons. Okay, it's like people going to the beach. You can go to this beach that's totally crowded, or the one that's empty, you're going to go to the empty one. Or the one that's less crowded. And electrons, like you and I, when they choose the way they're going to go, when they choose their path, they're going to take the path of least resistance. Okay? Path of least resistance. Not necessarily the shortest path. Nathan, can you demonstrate for me the path of least resistance to the door? So I'm assuming you chose not to go this way because his legs were in the way. Okay, so he took the path of least resistance. Now, I want you to take the shortest path back. Go back. Shortest path back. Where's your desk?
Like this.
Yeah, you just go right over the top, right? That's what you would do. You can go sit down. That's fine. Yeah, you would crawl right over the top of her desk. Now you can see that that's going to take a lot more energy and work to crawl over all those desks. It is the shortest path though, right? Yes?
Yeah.
Okay, so that's why electricity will flow through a metal wire before it will jump through the air. Going through the air is hard. That's not less resistance. Going through a wire is easy. That's why they put lightning rods on the tops of buildings. Instead of letting lightning hit the building wherever and go through the building to the ground, they give it an easier path. It goes to the rod instead. Okay? Yeah, he could have gone, right over the top, but that was not least resistance. So they'll take the easiest path, which isn't always the shortest one. Sometimes it's the shortest one, sometimes it's not. So whichever one is easiest. This last rule has to do with static electricity, and it talks about the larger the object is, the better it will be at storing electrons. Remember, any atom has electrons, almost all of them do, has the ability to give you electricity. Now you're understanding how you're able to get electricity from scuffing your feet on the carpet. That has the ability to give you electricity, this has the ability to give me electricity, but most objects are already neutral. You don't get shocked by your desk every time you sit down or by your shirt every time you put it on. They're usually neutral. Nature likes things nice and balanced. Okay? The ball rolls downhill and comes to a rest, comes to a stop at the end. It doesn't go, ooh, that was fun, and start rolling uphill. Okay? Nature likes things balanced. You go and you get shocked by touching the light plate, and that's it. The shock is over. It doesn't just build back up on its own. Things left alone tend to be neutral. Okay? So you're neutral, I'm neutral. Now, I take my shoes off, I scuff on the carpet with my socks, and I build up extra electrons. I'm actually knocking them off of the carpet. And they're building up, and they're collecting up on my body. I have extra electrons. Let's say I have 1,000. The number would be much greater, but let's say I have 1,000. And I come up to Mitchell, and I go to touch it. Are my electrons going to want to go to him?
Yeah.
Yeah. Okay? Remember? They're going to want to go to where there are fewer electrons. I have extra. I have 1,000 extra. He has no extra. So how many of mine are going to go to him?
500.
Excellent. So you get a star for that. You're the first one I heard answer. 500. Now, can you tell me why?
Because you already had full electrons, and so you already had 1,000 extra, and he had full. So then it's split in half.
Why wouldn't it be 1,000? Why wouldn't they all go over there? Nathan?
Because then when it evens out, they're not going to go there.
Exactly. They're going to move until it's even. If 1,000 went over to him, then he'd have 1,000 extra, and how many would I have? 0 extra. And they'd want to come right back. It'd be like this, guys. Imagine there's 1,000 people on the beach, and the lifeguards open up the new section of beach, and all 1,000 people get up and move to the new section and sit down. You haven't gained anything, right? You want to spread out. You want to go till there's 500 here and 500 there. Okay? And that's what happens. We're going to go until things are balanced out. You might have wondered, why is it that you get shocked so much worse when you go and you touch, say, a light plate, something that's metal? It's not just that it's metal. Okay? You could be holding something metal in your hand and you're not going to get shocked by it. But the answer is in this last one. It says the larger the uncharged object, the better it will be at storing electricity or electrons. What is the largest object on the Earth? It's a trick question. The Earth. The Earth is the largest object on the Earth. And if you've got, let's say, a metal pole, like that pipe, that goes right into the Earth, metal is a great thing for electrons to go through. That's why we make our wires out of metal. It's a great conductor, we say. If I build up a big charge on me and I come over here to touch something that's metal that goes into the earth, I've given it a great path, and the electrons would love to go there. The earth has a lot of space, can hold a lot of a charge. If you touch an electric plate, that's been wired by a wire to go to the earth for safety reasons. It will carry that charge off very quickly. It'll feel a very strong shock compared to touching someone else. Okay? So those rules, if you remember those and understand them, it'll really help you to predict what's going on. Like for instance, a balloon. You take a balloon, you rub it on your hair. You're giving it electrons. So the charge on the balloon is positive, negative, or neutral. You gave it electrons. What's its charge? Negative. Every electron has a negative charge. So you got a whole bunch of extra electrons on that balloon. Now do you understand why when you put it to the wall it sticks? Because the wall has what charge?
Positive. Neutral.
Neutral. It's connected to the earth. It doesn't have extra electrons. Most objects don't have extra electrons. So it sticks to the wall. And it takes a while because it's made of rubber and this is material that's not a good conductor. It takes a while for the electrons to move over. But once half of them move over, they're no longer attracted. Got equal number of electrons. And what happens with the balloon? Falls down. And that's why you see it may take a while, but eventually it falls back down to the ground. Because everything goes back to neutral. It's like a ball rolling downhill. Eventually everything will go back to nice, even Steven. Okay? Now on this side, we did not cover the last two here, or three, so don't worry about getting those definitions down. You should have all the other definitions down, though. Oops, hold on a sec.